Hi, I'm Ms. Fung. Today we're going to look at applications to probability in combinatorics. Previously, I've left you with a puzzle. Could you find a pattern with Pascal's triangle and NCR? Perhaps you did. Let's see if it's the same as what I have here for you. You would have noticed that C0C0 is equal to 1, and then 1C0 is equal to 1, and 1C1 is equal to 1. 2C0 is equal to 1, 2C1 is equal to 2, 2C2 is equal to 1. In other words, the row is n, C2, 1, that would be row 3, so be 3C0, 3C1, 3C2, 3C3, that will be n is 4, so 4C0, 4C1, 4C2, 4C3, 4C4, etc. And the order that I'm reading is R, so R is 0, R is 1, R is 2, R is 3, etc. Another thing you could have noticed is the row adds up to that last problem we came up with, pattern we came up with. So that is 2 to the 0, which is 1, 2 to the 1, which is 2, 2 to the 2 is 4, 1 plus 2 is plus 1 is 4, 2 to the 3 is 8, 1 plus 3 plus 3 plus 1 is 8. So the total of any number between 0 and n of combination is the sum of the row 2 to the n. Today we're going to look at probability. In summary, is what you want over what's available, the favorable outcomes over the total number of possible outcomes. Let's do an example. If Ella makes a guess as to which 2 out of 8 swimmers in Tokyo Olympics will come first and second in a race, what is the probability that her guess will be correct? Well, she has one guess, and the total possibilities are the number of ways 2 swimmers can be chosen from 8. The first question we always ask is, does order matter? First, second, order does matter. So do we choose P or C? We would choose P because order matters. So we have one guess, so 1 would go at the top, and we have 8P2. And that's because order matters. So that gives us 1 over 56. Example 2, four-letter codes. Example 2, 4-letter codes are to be made by arranging the letters oranges. What is the probability that the code will end with a vowel? So the probability of ending with a vowel would mean 4 letters that end with a vowel is what we want, over any 4 letters. So 4 letters ending with a vowel. So we want a vowel there, which is O, A, or E. So we have 3 choices. And then any, and any. So we have 6 choices left after we picked a letter. Then 5 choices and 4 choices. This and this and this and this means we multiply over any 4-letter code. So that means 1, 2, 3, 4, 5, 6, 7 letters can go there. And if we use 1 letter, we have 6. If we use 1 letter, we have 5. If we use 1 letter, we have 4. So 7 times 6 times 5 times 4. So the probability of ending with a vowel is 6 times 5 times 4 times 3 over 7 times 6 times 5 times 4. In other words, 3 over 7. Example 3. Say we have 4 donuts and 6 cupcakes, and 3 desserts are chosen. What is the probability that exactly 1 donut is chosen? So we're picking 3 desserts and 1 donut is what we want. So we want 1 donut, that means we have to pick 2 cupcakes, and out of any 3 desserts. Again, does order matter? No, it doesn't. So now, instead of using P, we have to use C. So we have 4C1 for the top, for the donut, and we have 6C2 for the cupcakes. And it's this and that, so it's times. For the bottom, we're picking any 3 desserts out of 10 desserts. So 10C3. So our answer should be 60 over 120, which simplifies to be 1 over 2. What if we had to pick 3 desserts and we wanted at least 2 donuts? Well, at least 2 donuts mean we have 2 donuts, or we are having 3 desserts, we can have all of them as being donuts. So we can have 2 donuts and 1 cupcake, or 3 donuts and no cupcakes. Be very careful that no cupcakes is placed in there as well. So that's what we want, and it's over any 3 desserts. Now I'm going to do the 3 desserts first because it's easy. That is, out of the 10 desserts, we're picking any 3. That's our denominator. The numerator is 2 donuts and 1 cupcakes. So order, again, doesn't matter, so we're doing C. So 2 donuts would be 4C2 and 1 cupcake, so 6C1. Or, that means plus 3 donuts, so 4C3. And, so times 0 cupcakes, 6C0. And we know that anything 0 is 1 anyway. So now if you plug that into the calculator, you will see that we obtain 1 over 3. Example 5. If the letters in education randomly interchange, what is the probability that the letters A and T end up next to each other? So we want A and T together over any random 9-letter arrangement. 9 letters because we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And we notice, are there anything that are the same? No repetition. That makes this question a lot easier. So again, we can have any 9 letters. That would be 9 factorial. Let's do the denominator first because it's easier. Now AT together, how would you treat AT together? Well, if AT is to be together, then we treat it as one group. 2, 3, 4, 5, 6, 7. So we have 8 groups altogether. And then we have to multiply by the different ways we can arrange AT, which is 2 factorial. So if you've forgotten how to do it together, watch the video that has restrictions. So 8 factorial over 9 factorial, well, 9 factorial is 9 times 8 factorial, so that cancels out. So you're left with 2 factorial over 9, or in other words, 2 over 9. Example 6. 8 people are given random seats about a circular table. So in a circle, what is the probability that 3 friends will find themselves next to each other? So 3 together is what we want in a circle over anything in a circle. So the 8 in a circle. Again, recall how to put things together in a circle. You can go back to the video on circles. So 8 in a circle, we have 8 objects, but when we're putting things together, we count it as 6 objects or 6 groups. 1, 2, 3, 4, 5, 6. So what do we have? The 8 in a circle would be 8 minus 1 factorial, because the circle formula is n minus 1 factorial. And then with 3 together, that will be 1, 2, 3. We said 6 groups, but in a circle, so 6 minus 1 factorial, times the different arrangements of ABC, which is 3 factorial. So now put that in the calculator and you should come up with 1 over 7. Thank you for watching, and you might want to watch the calculator examples, revise how to simplify factorials, and I'll see you next time. Bye!